Okay, let's discuss about concavity, second derivative test. Let f be differentiable in an interval I, and let c is the element of I with f prime c which equals to 0. If f double prime c less than 0, then f of c is a relative maximum value of f. If f double prime c greater than 0, then f of c is a relative minimum value of f. If f double prime c which equal to 0, then we cannot draw any conclusion about f of c. We can check also the practical examples on second derivative test. Let f of x is equals to x cubed minus 3x plus 1. First of all, we have a derivative. It's like this. F derivative at x must be 3x squared minus 3 which equals to 0. And then let's identify the critical number to factorize with it. Then f derivative at negative 1 must be 3 times negative 1 the whole square minus 3 which equal to 0. And f derivative at positive 1, 3 at the positive 1 the whole square minus 3 which equal to 0 also. Now we have identified the first derivative test. Second derivative test must be 6x after you derivate the first derivative. Then f double prime minus 1 must be 6 times minus 1 which equals to minus 6 less than 0. And f double prime 1 which equals to 6 times 1 must be 6 greater than 0. Let's compare the maximum and minimum value. Negative 6 of the f of prime double prime must be negative 1 if the minimum value, and f of prime 1 is must be maximum value. Optimization problems. A lot of practical problems can be expressed as a continuous function on a closed and bounded interval. We may be interested to find points where f attains its maximum or its minimum values. For instance, we may be interested in finding the maximum area of a region to be enclosed by fixed perimeter, the minimum distance from a fixed point to a curve. In economics, a function may represent a profit or cost function, and we may want to find the value of x to find maximum profit and minimum cost, and so on. The maximum minimum theorem and the first and second derivative test will be crucial in finding such points as are illustrated in the following examples. Here what I mean. In the example, a landowner wishes to use 2000 meters of fencing to enclose a rectangular region. Suppose one side of the land lies along a river and does not need fencing. What should be the sides of the region in order to maximize the area? Suppose the rectangle is to have length x and width y meters. We draw like this the rectangle. Here is x and there's 2y. X plus 2y which is equal to 2000. Reverse 2y and it's become negative. 2y over 2 must be 2000 minus x. 2y must be divided by both by 2. And 2 and 2 must be cancelled. Remain y which is equal to 1000 minus x over 2. Area of rectangle A which equals to xy. A which equals to x times 1000 minus x over 2 is 1000x minus x squared over 2. And we have here the maximum which is given 0 up to 2000 of the maximum here. But when we derivate it, 1000 minus x equals to 0. X equals to 1000. Y which is equal to 1000 minus x over 2. 1000 minus 500 must be 500. This is all about what we have identified. Thanks for listening.